But now what about products of disjoint cycles? What about the order of product of disjoint cycles? Okay, and this is dealt with the next, this is dealt by next proposition. It says that if sigma is an element of the symmetric group, has cycle decomposition let's say sigma equals sigma 1, sigma 2 up to sigma k. Okay, so and remember, cycle decomposition always assumes that the cycles are disjoint cycles. And let's say sigma 1, sigma I is a mi cycle. So in other words, sigma 1 is a cycle of length m1, sigma 2 is a cycle of length m2, sigma k is a cycle of length mk. Then order of sigma is LCM, least common multiple of m1, m2, mk. Okay, so proof. So first of all, LCM stands for least common multiple. So now we have, in the previous proposition, showed that if you have a single cycle, its order is the length of that cycle. So if it's a k cycle, its order is k. Now I am in the new proposition, I am telling you, if you have a cycle decomposition into a product of k cycles which are disjoint, that's important, and then the order of the product is the LCM of the individual orders. Remember, order of sigma I is mi, and the order of sigma is LCM of mi. So this is very easy to prove. Okay, so by the previous proposition, let's quickly prove this. By the previous proposition, order of sigma I is mi. So let's keep this in mind for I from 1 to k. So order of sigma I is mi, because sigma I is an mi cycle. So it has order mi. So let m be the LCM. Okay, so for simplicity, let capital M be the LCM of m1 through mk. Now, what is sigma power m? Let's compute sigma power m. This is sigma 1, sigma 2 up to sigma k power m. So remember, this means I am doing sigma 1 sigma k, sigma 1 sigma k, sigma 1 sigma k, m times, right? So this is sigma, this is sigma, sigma. In general, permutations do not commute with each other, but disjoint cycles do. So you can, sigma 1 sigma k is sigma k sigma 1, because they are disjoint cycles. Because they are disjoint cycles, we can interchange them, sigma, and in a group we can apply associativity law, so we can remove the brackets first. Sigma k and sigma 1 can be interchanged, and then you can reorganize all of them and put all sigma 1s to the beginning, so you get sigma 1 power m. Then you put all sigma 2s. Basically, commutativity of this sigma i's means that you can arrange them in any order. I'll put all sigma 1s first, there are m of them, then all sigma 2s, then all sigma 3s, and finally all sigma k's. Okay, so I can write this sigma power m as this. But now m is the LCM of mi, small mi. So order of sigma 1 is m1, and m1 divides capital M, because capital M is the LCM of m1 through mk. So in particular, m1 divides m. This implies sigma 1 power m is identity, right? This is something we have seen in detail in various situations. If you have order times something, power of that will be identity. Similarly, sigma 2 power m is also identity because m2 also divides m. m3 divides m, so that's E. So everything is E. So sigma power m is E. This means order of, remember, order of sigma is supposed to be m. So we have to prove that order of sigma is m. So in other words, the least positive integer d such that sigma power d is identity is m. We have checked that sigma power m is identity. We now need to check that nothing smaller than m can make identity. So suppose sigma power n is identity. Okay, by the same calculation above, so E is sigma power n, just like we calculated here. Because sigma 1, sigma 2, sigma k commute with each other, I can write sigma power n as sigma 1 power n, sigma 2 power n, sigma k power n. I can rearrange them so that all sigma 1s come first, sigma 2s come next, sigma 3s come next, and finally sigma k's come next. Now let's stare at this equation for a while. Remember, sigma 1, sigma 2, sigma k are disjoint cycles. So whatever index that appears in sigma 1 does not appear in sigma 2, does not appear in sigma 3. But after applying, so suppose I is an index appearing in sigma 1, then so I does not appear in sigma 2, sigma 3, right? Because sigma 1 is disjoint with sigma 2. I does not appear in, I appears in sigma 1, so it doesn't appear in sigma 2. Similarly, it doesn't appear in sigma 3 and sigma k. Now I claim that this implies I does not appear in sigma 2 power n also, sigma 3 power n also, sigma k power n also. Because remember, sigma 2 when you apply to itself, it only talks about, deals with indices that originally appear in sigma 2. In the previous examples, when we proved the previous proposition, remember, if you take 1, 2, 3, 5 as the cycle, its product with itself only involve the original indices that appear in sigma. In this example, it's 1, 2, 3, 5. So products will only involve 1, 2, 3, 5. Suddenly a new index cannot appear, right? Because sigma, if sigma fixes an index, powers of sigma continue to fix that index. So we don't have to worry about if I does not appear in sigma 2, I does not appear in sigma 2 squared, sigma 2 power 3, sigma 2 power n. So I only appears in, hence I only appears in sigma 1 power n, right? So I only appears in sigma power 1 power n. Maybe it doesn't appear in that also because it is fixed by I, but it can't appear in sigma 2 power n, sigma k power n. So now E fixes I, right? Because E is the identity element. So sigma n fixes I, because sigma power n is, so I'm assuming sigma power n is E for some n. Sigma power n fixes I. This implies sigma power 1, sigma 1 power n, sigma 2 power n, sigma k power n fixes I. We just argued in the right hand side of this slide that sigma 2 power n fixes I. If it doesn't appear in I means I doesn't appear in sigma 2 power n means it fixes I. Sigma k power n also fixes I. So we can conclude that only, so it fixes I. So sigma 1 power n fixes I. So sigma 1 power n must fix I. It cannot, see, if it sends I to something else, because I is not present in sigma 2 and sigma k, you can't send I back to itself under this product. So sigma 1 power n fixes I. Similarly, sigma 1 power n fixes every index appearing in sigma, right? So I was an index appearing sigma 1, appearing in sigma 1. If I was an index appearing in sigma 1, because sigma 2 power n, sigma 3 power n, sigma k power n, they all fix I, we can be sure that sigma 1 power n also fixes I, because if it doesn't fix I, the product cannot fix I. That is the point. Because if I goes to j, how will j come back to I? Under the product, it is supposed to come back to I. Under the product of sigma 1 power n, sigma 2 power n, sigma k power n, I goes to I. So if I goes to j under sigma 1 power n, j must come back to I, but it cannot, because j, if I doesn't appear in these indices, j also won't appear in these indices. So I must go to I under sigma 1 power n. Similarly, everything that appears in sigma 1 must be fixed by sigma 1. This is to say, sigma 1 power n is identity. So sigma 1 power n must fix everything that's in sigma 1. Of course, it fixes everything that's not in sigma 1, because sigma 1 fixes everything that's not in sigma 1. So sigma 1 power n is identity. It fixes every index. But then order of sigma 1 is m1 and sigma 1 power n is identity. These two together imply that m1 divides n, right? This is also an exercise I have done in the previous videos. If order of an element is m but some other power of that element is e, then the order must divide n. We have argued with sigma 1, we can argue with sigma 2. The same argument will show that sigma 2 power n is also identity, right? There is nothing special about sigma 1. Sigma 1 power n is identity means sigma 2 power n is also identity. So m2 divides n and so on. Order of sigma k is mk and sigma k power n is also identity by the same argument. So mk divides, so each mi divides n. Since each mi divides n for all I, we have the LCM divides n. See, if each mi divides n, n is a multiple, m is a common multiple of mi, right? But capital M is the least common multiple, and the property of least common multiples is that least common multiple divides all other multiples. And in fact, definitely we have, even if you don't agree with this or you are not familiar with this, it is the least common multiple. M is the least common multiple and n is a multiple, so we must have this. M is the least we only need this for the moment. Capital M is the least common multiple, n is a multiple, so m is less than or equal to n. So what we have shown is that, now coming back to our sigma power m is identity, and if sigma power n is identity for a positive integer n, then m is less than n. So together these two facts imply that order of sigma is m. So this proves the proposition. Right? What we have shown is that if you have a product of disjoint cycles, then order is the common multiple of the sizes, least common multiple of the orders of each individual disjoint cycle. So for example, if you take 1, 2, 4, the element we started with in the video, 1 3 2 4 5 6 7 8, right? So this has order 4, order 2, order 2. So what is order of sigma? And recall that these are disjoint cycles, which is important. So order is LCM of 4 2 2, which is 4. So order of sigma is 4. So as I said, it's important that the cycle have disjoint decomposition. The cycles are disjoint. Let's look at another example. Let's take sigma to be 1 2 and 1 2 3. Okay, these are not disjoint cycles. What is the order of this? In order to find that, let's multiply it out. Where does this go? This we have done before. 1 goes to 2, 2 goes to 1. So this is 1 is sent to itself. 2 goes to 3, and 3 goes to 1, and 1 goes to 3. So this is 2 3. So sigma is a 2 cycle, but it is a product of it is also a product of a 2 cycle and a 3 cycle. Sigma is a 2 cycle, but it's also a product of a 2 cycle 1 2 and 3 cycle 1 2 3. If the proposition applied to any product, order of sigma actually is 2 because it's a 2 cycle. And we have already proved in a previous proposition that k cycle is order k. So order of sigma is 2, but LCM of 2 and 3 is 6. 6 is different from 2, right? So the proposition requires that the cycles are here. The proposition does not apply because 1 2 and 1 2 3 are not disjoint cycles. So to find the order of a permutation, we have to find its disjoint cycle decomposition. If you have a sum cycle decomposition, you can't say order is LCM of the individual orders. So only if you have disjoint cycle decomposition, you have the property that order is the LCM of orders. Okay, so I'm going to stop the video in this at this point. In this video, we have looked at cycle notation for elements of symmetric group. We have seen that every element of symmetric group has a decomposition into disjoint product of cycles or product of disjoint cycles. We have seen that order of a k cycle is k, and we have seen that if you have a permutation as a decomposition into disjoint cycles, order of the permutation is LCM of the individual orders. In the next video, we are going to further study the cycle decomposition. Thank you.